Welcome to part 5. Let's get started. 3 important keywords. They define structures, classes, and protocols. Now they're all types. They all define types. And let's start with class. An instance of a class definition is referred to as an object. There can be multiple instances of objects. They all have a data model and functionality, so-called properties and methods. You can inherit one class from another and enhance the behavior. So you can extend behavior and you can instantiate an object. It will have that enhanced behavior. That's object-oriented, and I'm assuming you already know that. Structs can also have instances, right? Instance of a struct. Structures in Swift, unlike Objective-C, can also have behavior, which is new. There's a data model and behavior. Both classes and structs can also adopt protocols. Now, a protocol is really a set of requirements for what has to be implemented. It sort of defines an interface. Why a protocol is a type, you cannot have instances of protocols. Even though struct and class are similar, there are two and very important differences. You cannot use inheritance for structures. You can for classes. The second is where instances are stored. Structure is a value type, where class is a reference type. In other words, if you create an instance of a structure within a function, memory is placed on the stack. When the function ends, that data is released, that storage is released. When you create an object, you get a reference to that object, and the object is placed on the heap. So there is overhead. It's a little bit more expensive. However, you can have multiple references to that class. Now, Swift, like Objective-C, uses automatic reference counting. So if all the references go away to the class, then that memory is released. Let's move on and look at the examples and check out the syntax. I'm going to define a structure here called point, and it's going to have an x and y value, which are a double, and you'll notice the syntax here. If you have two variables of the same type, you can combine them in this line shown. It's simply going to have a function called test. Now, in the past, structures couldn't have functionality, or instances of structures couldn't have functionality. I'm going to create a point by calling this initializer with the value of x and y. That initializer is created for you for free by the compiler. I can take that PT variable and I can invoke the test functionality. If I set another point, pt2, to pt, pt2 is assumed to be of type point because it's assumed typing. There's now two instances of that structure is copied. Now, what I'm doing here in the last line is I'm trying something different. What I'm trying to do, instantiate a point with no arguments. Now, the reason I'm getting an error in that case is that there's no initial values for x and y. In the structure definition, if I said x equal to 0, for instance, and y equal to 0, then it would be possible to create a point with no arguments, and it would actually be the origin. Now, if I want to make a point that's a class, I have similar syntax here. However, I don't get the free initializer. I have to define one. And the arguments are the same, x and y. And I'm using the same name for the arguments as I am for the properties. So I have to be a little careful here. Self.x refers to the variable within the object. Simply x refers to the argument passed to the init. So self.x equals x, and similarly for the y. There's also the notion of a dinit. Now you notice there's no func in front of these things. They're special case implementations. dinit is invoked when a object, an instance of this class, is removed from the heap. In other words, when all references go away and the count goes to 0. Now there's an example of that down here. I'm creating a point. I'm instantiating it with the initializer I defined. And I go and reuse that reference and create yet another point, different instance. Now what happens is the first point is no longer referenced. So what happens is the dinit is actually invoked, and you see that via the print statement. Now protocols. Protocol defines a set of requirements, and classes can adopt protocols. In this case, I have the notion of a shape, and the shape has to have a function. Like a class that adopts the protocol shape has to have a function area which returns a double. Now I have a class rectangle which adopts the shape protocol. It has a similar x and y double, which is actually length and width. I have an initializer. You've seen this before. And I have a function area which I'm required to implement, and it mathematically returns basically the length versus the width. I probably should have used length and width as the names rather than x and y. The following is just obviously making use of what I just implemented. Now, let's talk about inheritance. I have class A, which defines a method, basically a function, test. I have a class B, which inherits from A. Now, I want to change the functionality performed by the test function. I want to extend it, for example. So I override it. I say I want to modify this. Now, at the same time, I may want to also invoke the functionality provided by the base class. And I can do that by saying super.test. It's very much the same in Objective-C. And I extend the functionality by doing a print. Now, this whole thing brings up an interesting question about syntax. In this case, I have a protocol P, empty, and I simply have an empty class A. Now, I have a class B that adopts the protocol P. But in the C case, I want to inherit from A, but I also want to adopt P. Now keep in mind, like Objective-C. Swift only supports single inheritance, so you can't inherit from multiple classes. Now, syntactically here, the first type after the colon can either be a class or a protocol. If it's a class, comma, you follow with one or more protocols. If the first is a protocol, you can't specify a class. In other words, the class has to come first. This is the last for part 5. Stay tuned for part 6.